Well, one last interesting application that we can think of right here is something called simple harmonic motion. And by definition, they tell you this: a point that moves along a coordinate line is said to be in simple harmonic motion if its distance d from the origin at time t is given by either d equals a times the sine of omega, that's the Greek letter omega, not wt, or d equals a times the cosine of omega t, where a and omega are real numbers such that omega is always greater than 0. The motion has amplitude absolute value of a, period of 2 pi over omega, there's a surprise, right? And a frequency of omega over 2 pi. Frequency is defined sometimes as 1 over the period. All right. Well, let's talk about an example. What exactly does that mean, simple harmonic motion? Well, assume that we've got, let's say, a weight attached to a spring, right? This is sort of the typical model. And you just hang that weight at the end of the spring. And the spring, we don't have any motion on the spring right now, right? We just have a weight attached to that spring, all right? Whatever the weight is, right? Now, somebody comes along and decides to pull that spring, right? So in the next step, they decide to pull that spring so that we stretch everything out, right? We stretch it out to the limit of its length, right? Okay, so here's our weight now attached to the bottom of that spring, okay? And we just let that weight go. What's going to happen? Well, we know what's going to happen right here, right? The spring is going to bounce up and down, right? It's had a resting position, but it's stretched out below. Now it's going to have this very squashed position that it comes up to all the way at the top of where it can go. And then it's going to come back down, right? And then it's just going to keep bouncing back and forth so that we have a displacement position that is almost equally as high as it is low above, but it works along a straight line right here, right? And so this simple harmonic motion bounces up and down this way constantly according to one of these formulas right here, right? When we say, let's say that for the simple harmonic motion we described here, let's say that we have the function d, our distance, is given as 9 times the cosine of 6 pi over 5t. All right, so our distance d, we're saying, well, our distance d right here above, right, we're saying that's equal to the distance below. So we're going to call that distance d, right? That distance right here at any given point above its resting point, which goes right along the middle here, right at time t equals 0, looks like this, right? So our model goes like d equals 9 cosine is 6 pi over 5t. So we might come up as high as 9 or as low as 9 below that center axis right here that we would have. Only at time t equals 0, I think in this model, we're actually starting at the top and we're letting it drop down. But there's some middle position right here. All right, what could we say? Well, what is the maximum displacement? The maximum displacement, the maximum displacement has to deal with the amount d we go above or below this resting position. So in this case, we're going to say it's 9. Let's say it goes in centimeters here, right? Let's just leave it as centimeters. We're going to assume, although we're not really told. So it's just 9 is really the number that's important to us. Okay, that's the maximum displacement. Now, of course, how far does it travel up and down? We can say that the total displacement then is going to be equal to 18 centimeters, right? 9 centimeters is just the maximum displacement right here from its center position. We want to know the frequency. Well, what is the frequency? Well, we said that the frequency is found by taking omega divided by 2 pi. So we could think of it this way. If we had a function like this, we were usually interested in finding the period, and we found the period by taking 2 pi and dividing it by whatever number was multiplied by t, right? The period would be 6 pi over 5. So working that out, we're going to end up with 5/3. So our frequency is the reciprocal of that, 3/5. Right? Our frequency, I guess, could be stated as 3 for 5 every cycle right here. Uh, what are we going to say about our value of d when t equals 5? Well, let's try it out. If we want to find our displacement at time t equals 5, then we would take 9 times the cosine of 6 pi over 5 and multiply that by 5, right? So we're taking the cosine of 6 pi over 5 times 5, so our displacement would be 9 times the cosine of 6 pi. So that's interesting. What happens at 6 pi? Well, 6 pi is coterminal with 2 pi. And we know that cosine, and 2 pi, of course, is coterminal with 0, right? The cosine of 0, or 2 pi, is equal to 1. So d, our distance, is going to be 9 times 1, or just 9. Finally, what is the least positive value of t for which d is equal to 0? Where would d equal 0? Well, now this last part's a little bit harder, but let's see. Here's part B. Here's part C. Right? So let's go to part D here. This is A. Part D. What we should do is we should set 9 times the cosine of 6 pi over 5 t equal to 0 and solve for t if that's at all possible. All right. Well, dividing both sides by 9 just gives us cosine of the quantity 6 pi t over 5, or 6/5 t, equal to 0. So we ask the question, where does cosine equal 0? Well, we know that cosine equals 0 for angles that are pi over 2 or odd multiples of pi over 2. Remember our trigonometric functions, right? When we're talking about secant and we're talking about sine, right? So 6 pi over 5t will equal pi over 2 as the lowest possible value where cosine is equal to 0. So we have to solve for t in this case. T would be equal to pi over 2 times 5 over 6 pi. And working that out gives us t equals 5/12. So if this is in seconds, at 5/12 is a second, it will be the first position in which the distance is equal to 0. Right? So in other words, we have this spring, we let it go at its top of its little squashed up path right here, drops down 5/12 of a second later, it's at that middle. And then so on, bounces back and forth between those points. All right, good luck with your work. I'll see you in class.